provable because sigma is an equivalence relation. You can apply the reflexivity here, and sigma is also subset of rho composite sigma, because both sigma and rho, they are equivalence relations. This is always they are actually equivalence relation. Like you can apply here reflexivity and transitivity, and you will see that rho is subset of rho composite sigma, sigma is subset of rho composite sigma. Now let's see the union actually. What about the union? Their union will be subset of the same relation because they are subset of rho union sigma subset of rho composite sigma. So if you apply this n times, and you will see that rho union sigma power n, rho union sigma power n, it will be subset of rho composite sigma power n, and then you will see like infinite here, you will see that this infinity rho union sigma power infinity will be subset of rho composite sigma power infinity. But this we have seen that in star, rho union sigma power infinity is actually it's equal to rho join sigma, which is subset of rho composite sigma power infinity. So name it A, this one, and name it P. From A and B, we conclude that rho join sigma is equal to rho composition sigma infinity. Okay. From A and B, we conclude that from A and B, we conclude that rho join sigma is equal to rho composition sigma infinity. This is a very important relation. Now, what is this actually? By definition, it's actually union. N runs from 1 to infinity. Rho composition sigma power n. Okay. Now look at this. Now let's take any element here. Now that AB belongs. Now we come to the proof of the theorem. This is true if and only if it belongs to the union. Union means there exists n belongs to n, such that A comma B belongs to rho composition sigma power n. So now you can expand this. It's rho composition sigma composition, rho composition sigma composition n times rho composition sigma. Now by definition of the composition, there exists, thus this is true if and only if there exists x1, x2 so on up to x2 n minus 1 in S, such that A comma x1 belongs to first one, A comma x1 belongs to this rho, and the second this x1 comma x2. This is the definition of composition actually, belongs to sigma. The next one x2 x3, it belongs to the next relation, that's rho here, and the next which belongs to sigma. You can continue this process and you will see this x2n minus 2 comma x2n minus 1, it will belong to that one rho, and finally x2n minus 1 comma b, it belongs to sigma. So this proves the theorem completely. A and B belongs to rho join sigma if and only if there exists n belongs to n such that this holds. Now an important theorem here, it's actually corollary of this previous theorem. It states that let rho and sigma be equivalence on a set or congruences, be equivalences on a set S, or you can say concurrences on a semigroup S. On a semigroup S. On a semigroup S. Such that rho composition sigma is equal to sigma composition rho. That's there, they commute under this composition relation. Then this join is nothing, it's just composition. So important. The smallest congruence containing or smallest equivalence containing rho and sigma is just their composition. In case they commute. So proof is very simple. It follows from previous theorem, and I will leave the proof here, and you can see the proof at page number 29 of the book of Hobby. Okay, fundamentals of theory of semigroups. You can see the proof. So it's not too difficult. You can see it. In case the congruences or equivalences, in case they commute, then the least upper bound of these two equivalences or these two congruences will be equal to the composition of the congruences or equivalences. It's very simple. Now we define ideal. Then we come to this Green's equivalences. Green's equivalence. First we define an ideal. The ideal of a semigroup. Let S be a semigroup. Let S be a semigroup. And I be a sub-semigroup of S. So first it should be a sub-semigroup. Be a sub-semigroup of S, not a necessary sub-semigroup. Be a non-empty set, you can say. Then be not equal to 5. It's subset of S. Okay. Then I is said to be first left ideal of S. If for all S belongs to S, U belongs to I, implies SU belongs to I. Second, it is said to be right ideal. Right ideal of S if for all S belongs to S, said to be a left ideal, a right ideal. For all U belongs to I, implies US belongs to I. And it is said to be an ideal. Ideal of S if it is both. If it's both left ideal and right ideal of S. That's the definition of ideal of a semigroup. Okay, now we come to Green's equivalences. So there are some equivalences which we call the Green's equivalence. Equivalence means the relation actually. Green's equivalences. So these relations are very important in theory of semigroups. Okay. Let's first define principal ideal. Let S be a semigroup and A belongs to S. A belongs to S. A belongs to S. A belongs to S. Then the smallest left ideal. The smallest smallest left ideal, smallest left ideal of S of F containing A, which contains this element A, is SA union A. So SA means this set. SA means SA such that S belongs to S union singleton A. It's the left ideal, you can see, and it contains, and this is the smallest left ideal containing A, and is denoted by, and is denoted by S1A. This is notation. S1A means actually SA union this singleton. Or you can directly see this S1A is actually exactly equal to this. The elements of S1 into A, it will also contain A and those elements as well, because S1 contains identity. So we denote it by this, and we call it the principal left ideal generated by the principal left ideal generated by the set by element A, generated by A. So equivalently we can define the principal right ideal. Similarly this SA sorry, it's not SA, it will be AS union A, which will denote by AS1 is called the principal right ideal of S containing A. So it's the smallest right ideal containing A. It's called the principal right ideal. Smallest right ideal containing A, that we call the principal right ideal of S containing A. Now, based on these ideals, principal left ideal and right ideal, we will define equivalences, and those equivalences we call the Green's equivalences. And first Green's equivalence is L relation, and second is the R relation. Both are equivalences, and then we see their intersection, which is also an equivalence, and then we see their join. They are very important relations. Their intersection, their joins, they are all important relations, and they are all given by Green's. So let's define L relation. An equivalence. An equivalence which we denote by L on S is defined by the rule this A is L related to B if and only if the principal left ideals generated by A and B they coincide. If and only if S1A is same as S1B. So if and only if they generate the same left ideal, then we can say they are L related. They are L related. If and only if they generate the same left ideal. Similarly, we define an equivalence which we are on S is defined by the rule A is R related to B if and only if they generate the same principal right ideals is same as B. BS1, AS1 is same as BS1. Now, in the next theorem, we characterize this relation in terms of the equations. Okay, that's the next theorem. Next theorem. Okay, this theorem. In this theorem, we'll see the equivalent form of above relations L and R. Let A comma B, they belong to the semigroup S. A comma B belongs to S, where S is a semigroup. Where S is a semigroup. Then A is related to P. Is related to B if and only if there exist X comma Y belongs to S1 such that XA is equal to B and YB is equal to A. Also, the R relation, the A is R related to B if and only if there exists U comma V belongs to S1. U comma V belongs to S1 such that UA is equal to B and this VB is equal to A. Okay. VB. Okay. Sorry, it's here X on left side and this is the left relation, and here it's AU actually. U should be on right side, and B also should be on right side. They are all related. So this is the theorem which gives the equivalent form of above relations L and R, and we'll use instead of this the definition of L in terms of the principal ideals, we'll use these equations in future. Okay, so let's do. I will prove on one part say L, or I can prove R. So let's prove this. Suppose A is L related to B. This implies S1A is equal to S1B. Now since A is here, or you can say since B belongs to now, B belongs to S1B. Because B is equal to 1 into B, but that's same as S1A. So therefore B S1A. So B is actually equal to the element of S into A. So thus there exists X in S1 such that B is equal to XA. B is equal to XA. Now A belongs to S1A, which is same as S1B, and that implies same as S1B, so which implies thus this A is also an S1B. There exists say Y belongs to S1 such that A is equal to YB. So therefore there exists, whenever A and B they are L related, therefore there exists X comma Y in S1 such that XA is equal to B and YB is equal to A. And converse is very simple. That's simple. So now you can see on the other part that A is R related to B. It is also simple. Thank you.